Very good evening to everyone. Till the last seven classes, we discussed enough on big data and various steps in the data science life cycle until the data modeling using some functions that help us to fit the data points. We started discussing on simple linear regression, multiple linear regression, and then we ended up our discussion with gradient descent, stochastic gradient descent, and so on. We have yet to go some more topics to finish the machine learning part. However, the neural network and deep learning will be handled by another professor in the upcoming weeks. Anyway, I will record this lecture and then upload. I have planned four lectures, unless I miss my guess. Today's lecture, we are going to discuss polynomial regression, and there are four confusing terminologies: overfitting, underfitting, bias, variance, and then lasso and ridge regression. Then we will see how to store and retrieve the model which we build during our coding. Then we will discuss one hot encoding for multiple regression. Finally, we will end discussion on some of the exercises in polynomial regression. So you will have to finish the exercise and then submit to me as usual. All right, let's start discussion on polynomial regression. So in the supervised learning, this is the third part. With this, we will finish off the regression completely. We will discuss the polynomial regression as I already told you, overfitting, underfitting, bias, variance, and then tuning hyperparameters. We will understand what hyperparameter is and how to tune it. What should be the criteria for being a good fit? We will see that. Then regularization, which is highly used in neural network and all those things. Then under which we discuss three topics: ridge regression, lasso, and elastic net regression. After completing this, you will be able to understand polynomial regression and these confusing terminologies very easily, and then work out some regularization methods with some pre-processing like one hot encoding. Polynomial regression. What is polynomial regression and why should we go to polynomial regression? It's a mathematical concept, but let us understand in simple way. Most of the time we try to fit a straight line for the data points. For example, we have measurements for mouse weight and size. After collecting some data, feature X and feature Y, I plot like a scatter plot. Then upon seeing this, I decide what kind of mathematical function that can be fit on the shape of this data points. Initially, I decide maybe a line model which is linear can fit very nicely. However, there is a calculation SSE that determines whether the line model is good enough or not. However, there are other options. You see, can I fit a curve like this? This is called log function. Okay, so when you plot log function, you will get the same shape. And can we fit like this? This is called exponential function. If you plot exponential function, you will get this kind of shape, and so on. Suppose you see a data points like this. A scenario is this is called the power consumption text feature, and this is electricity, or we can say outside temperature. Okay. Now, in one scenario, the if outside temperature is high, okay, then power consumption is also high. Maybe we can take it in different way. Uh, this is power. Maybe more meaningful, we can do like this. And this is outside temperature. Okay, room temperature or outside temperature. Now, when temperature is very least, say -1, -2, we will tend to use more power because of room heating and all other things. When temperature comes normal, we don't use much electricity because the temperature is good and we don't use anything, either AC or the heating. But when temperature increases, we will tend to use more electricity, so the power consumption becomes higher. Now, this relationship, temperature and power relationship, gives data points like this. So with this, we can't fit a straight line like this. Instead, we have to fit a curvy line like this. Okay, curvy line like this. And this is a quadratic function. For example, say ax square. All right. So with this function, I can draw this line and fit upon these data points. All right. Now I can even go more crazy thinking on different kind of function like this, fitting a data very nicely so that I can make good predictions. I can even do like this. This is called polynomial in general. Okay. So this is the reason we go into polynomial regression based on the shape or pattern of data points that exist on the Cartesian plane. All right. So, however, there is a deterministic measure called SSE that will decide whether I should take a line model on data points or something like this, polynomial models. So there are many applications that provide this kind of behavior: electricity consumption based outside temperature, growth rate of tissues, progression of disease epidemics, distribution of carbon isotopes, and so on. Especially such kind of abnormal or different data points, different shape of the data points may occur in science field like physics, chemistry, and so on. All right. In a normal in engineering way, we don't get such a different pattern like this. All right. So fitting a model depends on the shape of or pattern of the data points that project on the Cartesian plane. If the pattern seems parabola, then we have to use quadratic equation. We will see in the code how to fit a quadratic equation. Especially, there are three components or three terms in the quadratic equation: ax square plus bx plus c. Should I use all these three terms in order to fit a quadratic function, or should I use only these two, or should I use only one term? So this is also a deciding factor for the shape that we are going to fit. All right. So polynomial regression, in short, mapping independent variable or feature x and dependent variable feature y with nth degree polynomial. All right. So we understood the requirement of polynomial regression and different fitting style of a function. Now we need to understand polynomial and what is nth degree polynomial so that we will be very clear with polynomial regression. Now, how would I fit a polynomial function on the data points? First, let's understand this and then go into uh, detail of the polynomial. Now, on parabola data points pattern, to fit ax square plus bx plus c, this is the function I want to fit on these data points. Assume that the red color curve is not available, and we need to estimate the red color curvy line from these data points. So what I need to do, this is the function. X is the input feature in both terms. The coefficients or parameters A, B, and C are those three coefficients must be estimated or approximated from the data points X and Y. This is X, this is Y. So we need to find the value of A, B, C. That's it. If we find the value of A, B, C from the data points, then we will get our polynomial function that can fit on data points. All right. But we need to think whether the subordinate terms in polynomial function, we will always say subordinate terms in the sense if we have ax square plus bx plus c, the subordinate terms for x square is bx plus c. So we need to decide whether we have to include bx plus c. If we include, then we have to estimate the value for parameter b and c. So we have to find and then we have to come up with the model. Similarly, similarly like quadratic equation, we can fit log equation. Log in the sense you will get like this log and then x. This is by default 10. Okay, so you need to find what should be the value in the log. You have to, for example, ax, you have to estimate a. Similarly, exponential function e power ax. So what should be, in general we always study e power x, but we have to say the x is accompanied by the value 1. Am I right? So e power ax. By default this is 1, so we always say e power x. Now we need to find what is the value of a so that the function can fit nicely on these data points. That's how it is. But in the very worst case, we can fit a line that is so crazy like this. Okay, we don't know which equation is really used to represent this line as you see here, but we should go definitely like this: a x power 4 plus a or bx cube minus cx square and so on. Okay, dx plus e. Now assume that this function represents this curve. So what should I do in order to come up with the model? I have to estimate the value of a and b, c, d, and then e from the data point x and y. That's it. If you're able to find the value for these coefficients, then you will accomplish polynomial regression. That's it. Sometimes by using some algorithms like ridge lasso regression, automatically some coefficients or parameters will be turned into zero. Okay, so in that case, if the value of c is 0, then this term will be eliminated, and this term will be eliminated, and this term may be eliminated, and so on. Sometimes in neural network, there is a concept called dropout. We sometimes manually do it, sometimes automatically the dropout is done. Is just like this: by making the parameter to be 0, the entire term becomes 0. That's it. This is called fitting polynomial function on the data points. Okay, now you understood roughly how we fit the polynomial function on the data points and what does it mean really. Okay, the general equation, polynomial equation is this. Here, initially we start with b0, then b1 x, b2 x square, b3 x3 until bm x power m. So we have to decide some terms from this polynomial equation and we have to decide which function fits the data points nicely. So we have to determine the order or power. Okay, so this is called order or power of a term. So we need to determine which order is required. That is based on the shape of the data point. See, in this shape, we can directly observe that it looks like a parabola. So if the data points look like parabola, then in the quadratic equation, it is enough using only ax square. You need not use bx plus c. Okay, because while using bx plus c, the curve will bend again. So we need we need not use bx plus c. So enough using ax square. So it is up to us to determine how many terms to include in a polynomial and the order of the polynomial. So we have to be very cautious in choosing right model for fitting such kind of non-linear pattern or irregular patterns. Okay, so this is called polynomial pattern fitting. Next, is it non-linear regression? We always talk about linear regression, fitting a line. Since we are fitting log, exponential, and quadratic, should it be called non-linear regression? Okay, let us understand first what is polynomial and how we say linear or non-linear. If we understood that, we will understand why is it is not called as nonlinear regression. First, what is polynomial? An equation involving many terms. In general, it is a polynomial. So we need not mind what type of terms we are including. If an equation like y equal to e power x and minus e power x and 3x cube minus log x, it is a polynomial because it involves many terms. Easy. And then we need to understand power or order. So whatever is raised to a term, to a number, or to a constant, it is called power or order. Okay. So if a power is more than one or the negative value, then it is called nonlinear function. Okay. If some terms to be, or if an equation to be called as nonlinear, then its power the value of x should be greater than 1 or the negative value, or it can be any complex number like root x or log or whatever. All right. So we understood what is non-linear in an equation. Now, non-linear regression or non-linear function, how should we call this? First, we are not going to solve the value of x. For example, let me take a quadratic function ax square plus bx plus c. Here, my objective is to estimate the value of parameters a, b, and c. Remember, I'm not going to solve x. Okay, in general, in mathematical equation, we will call like this, say x square plus 6x plus say 3 and then 6. Now, how do we do that? This will result two values or two solution, maybe 2 and 3, for example. Okay, this is the solution of this equation. So here we are not doing that. X is always there, but we are going to estimate the value of A, B, and C. Here, X indicates the input feature that will take different values. Am I right? Input feature. Since we are not going to solve the variable x, instead we are going to estimate the value of parameters a, b, c. This is the reason we don't call fitting such a nonlinear function as a nonlinear regression. Still, the polynomial regression is a linear regression because the order of parameter is 1. We can say a equivalent to a power 1. Am I right? So the order is always 1. So remember, polynomial regression is a linear regression, even though we fit nonlinear function on the data points. All right, that's it. You understood the between the nonlinear function and nonlinear regression. Okay. All right. You have any doubts?
No.
Okay, great. Roughly, we can call polynomial regression as a nonlinear function fitting instead of wrongly calling polynomial or polynomial regression like a nonlinear regression. So instead of calling nonlinear regression by mistake, we can call nonlinear function fitting to denote the polynomial regression. That's all about understanding the polynomial regression. Now, how to determine the value of m in a polynomial equation? You understood the general equation as you see here. If you say a polynomial equation, you can extend up to m order. The order of m can be anything. But based on the shape or pattern of data points that appear in the Cartesian plane, you have to decide the order of polynomial. Once you decided the order of polynomial, you have to decide number of terms in the equation. Okay, so let me put like this. I'm going to decide the order 2 quadratic equation. Now I decided this is the typical equation. Okay, now I should decide whether I should include this term and this term or combination of this term, or should I remove these terms, and so on. All right. So these are the two objectives when we are working with polynomial regression. When the m value increases monotonically, monotonic in the sense constant increase, always added by 1. So such a line you see, okay, constant increase is called monotonically increase. The monotonically increasing m value keeps reducing the error. Hopefully you would have understood the SSE. We need to minimize, right? But beyond a point, that will also start increasing the error. That we will understand when we discuss about underfitting and overfitting. All right. So that's all about increasing the m value. Now higher order m, if I increased instead of fitting with the quadratic equation, if I try to fit with the polynomial that is taking the power 10, may fit all the data points. If there are 1,000 data points in training set, it will touch all the 1,000 points. If you keep increasing the value of m, that will lead to a problem called overfitting. Okay, overfitting. Now determining m value and determining the number of terms to include in the polynomial equation, it's a really headache because we have to try with each and every term, each and every order, and it takes a lot of time to decide what kind of function to be fitting on the data point. For that reason, we go to neural network. Okay, here where we exhaust fitting some function on the data point. Hereafter, I don't want to try myself because it already ate up my 1 month, 2 month time. Now I go to neural network. The neural network will give me the solution in just few minutes. Okay, this is the reason we go for neural network. So the objective of neural network is to fit nonlinear function on data point. Okay, nonlinear function or nonlinear pattern. Now, unlike polynomial equation that we use in polynomial regression, the neural network doesn't use polynomial function. Instead, it uses some kind of parameter called weight and bias. Okay, weight is a matrix, bias is also a vector, either row or column wise. So the value which we find after the gradient descent or so many concept, these matrices is the outcome of neural network instead of the coefficient value in polynomial regression. So what is the outcome of polynomial regression? Ax square plus bx plus c. The estimated value of a, b, c. This is the outcome of polynomial regression. But in neural network, the matrix value is the outcome of polynomial regression. To better understand, in neural network, we have so many layers, so many neurons. Each neuron corresponds to some value in the weight. So these weights all together in neural network determine a kind of non-linear shape. Okay, here weight plus bias is a simple addition operation, or this can be called polynomial order 1, say ax plus b. X is a input, and you see like this b and then a. All right, so with simple line we are going to fit a non-linear pattern. For example, how neural network works, let me explain. Now this is the quadratic equation parabola. All right. Now, for this, I can come up with the equation if it is a polynomial regression, ax square. And I found the value of a. The a is 5 and x square. X is the input. And this is all about polynomial regression. Now, with respect to neural network, what I would do, I don't explain now the matrices, but how it behaves, I explain. Now, it uses straight line. Neural network uses only linear regression. In fact, in linear regression we always use straight line. Okay, straight line like this. Now to fit a same kind, the neural network uses straight line like this. like this. Okay, everything is aligned, there is no curve. This is how it is done in the neural network, by adding many functions together, subtracting the functions together, and so on. Actually, the function is just like a matrices. Hope you understand now. Okay, if you don't understand, when you take the neural network course, you will understand so many things weights by us. Polynomial regression is so sensitive to the outliers, in the sense, outlier kind of a noise, and that outstands all other data point. If there are some outliers in the polynomial regression, it is highly affected and it causes to overfitting. Overfitting, I will explain in detail in the next slide, next page. Okay. So presence of one or two outliers is good enough in disturbing the entire polynomial regression. So pre-processing is must with polynomial regression. We have to do exploratory data analysis very nicely. What are the techniques that we use? We can use the box plot. You remember box plot? And then we can use scatter plot to determine the outliers. Next, overfitting, underfitting. It's so interesting and easy to understand. Now, look at this figure. Wherever the blue color data points, it's called training set. Okay, training data points, blue color. And green color is a testing data set. Okay, there is a data set and we split into two, training and testing. Blue color is training, green color is testing. The first column, okay, first column, this is fitting a line during training time, fitting a line during testing time. And the second column, fitting a polynomial equation. Sometimes instead of saying polynomial, we can say squiggle. Okay, squiggle means that a polynomial function. So I will use squiggle instead of polynomial. Now this one is squiggle in the training time, squiggle in the testing time. Now, upon seeing this figure, we always come up with some conclusion. To make that conclusion, we have to find sum of squared error during the training time for linear model, sum of square during the testing time of the linear model. Similarly, sum of squared error for squiggle during training time, sum of squared error for squiggle in testing time. So with this value, we will come to so many conclusions. The first conclusion, see, this is training for line. This is training for squiggle. Now, sum of squared error for the line is higher than sum of squared error for the squiggle. Why? You see the squiggle, it passes through all the data points. So there is no difference. Here the sum of squared error definitely must be 0 because there is no distance. In contrast, if you look at the linear model, there you see some error. This is a predicted value and this is the original value and the difference is called error. So there happens some error. Now, at least some say 50 is sum of squared error during the line. So during training phase, squiggle outperforms the line. So squiggle wins here. Now let's go to testing side. When I test with test data set, the squiggle sum of squared error is high. So this is the the prediction function, and this is the original data point in the test set. You see, my prediction line gives the answer here, but the original answer is here, the distance. And here is the distance. Here is the distance, which is the error. Here is the distance. My prediction line gives out the outcome here, but the original outcome is here. This is the error. Now, say sum of squared error of the squiggle might be some 40, but if you see here, still there are some error with linear model, but it would not be definitely beyond what squiggle produces. It might be 20. So during testing time, the linear model outperforms the squiggle because the sum of squared error is very less in linear model. So it's a basic understanding about sum of squared error in training and testing for two different models, linear and squiggle. All right. So hope you don't get confused with this. With this, we will advance to overfitting and underfitting. Now, what is overfitting? Okay, what is overfitting? Now consider this: if sum of squared error, if sum of squared error of squiggle during training time is very lesser than sum of squared error of squiggle during testing time. So if this condition is met, then it is called overfitting. All right. Here, absolutely the error will be zero. All right, zero. Here, absolutely the sum of squared error will be over 20. For example, take 20. Now, the zero is lesser, way lesser than 20. Am I right? So, sum of squared error during training time, sum of squared error during testing time. So, if this condition is met, it is called overfit. Why we say it is overfit? Training time, it fits very nicely. So, there is very least error or no error at all. But testing time, it doesn't fit the data point very well, so that it produces more sum of squared error. So there seems some problem during training time. Despite it fits well, it doesn't fit well on the testing data set. This is the reason we say overfit. Already you fit very nicely with training. That is the reason you don't fit very nicely with the testing set. That's the reason we say it is overfit. To avoid overfitting, there are some ways. One is increase the number of records. Say this data set contains only 10 samples or 10 records. Instead, increase number of records to 1000. If this is the case, the training set might contain 800 data points and testing set might contain 200 data points. So it would be nice to minimize the overfitting. And the second way is add some penalty to sum of squared error function. That's called regularization. So regularization is to avoid overfitting by adding some penalty in the error calculation function. That's it. So if somebody asks you what is regularization, this is the answer. All right. That's it. Let's understand underfitting. Now reverse the condition. For example, if sum of squared error is greater than sum of squared error during training time is greater than sum of squared error during testing time. It's called underfit. Okay. So during the training time, my sum of squared error is 20. On believing this, I go to testing side and I calculated sum of squared error. So this time the testing side produces say 10. Now you see that testing during training time it did not perform well, but testing time it performed well. So there seems some problem. This is called underfit. Why I say underfit? If I'm able to reduce the sum of squared error from 20 to way below to less than 10, then it means that the function has fit very nicely so that it minimized the error. But because it is 20, the function did not fit properly so that it causes more error. That is the reason we say underfit. So overfit, the sum of squared error during training time is very lesser than sum of squared error in the testing time. Underfit, the sum of squared error during training time is way higher than the sum of squared error during testing time. That's it. So if this condition you understood, then it is so easy. So the goal of machine learning is to fit training data and testing data very well. Why I have put double greater than? It is enough to put one greater than symbol. You should have asked, because I say way lesser than. So it's if I find the error, sum of squared error in training time is 20 and testing time it is just 22, then it's not a big deal. So it's just 2. If I put double greater than, it is way higher. In the sense 20 is way higher than 5. So there seems some problem. 5 is very different than 20. Okay, 15. The distance is 15. That is the reason I put like this. So the goal of machine learning is to fit training and testing set very well so that the prediction is better. So I need to find the sweet spot between underfit and overfit. Okay, somewhere between underfit and overfit, so that my sum of squared error in training and testing time, they are almost equal or approximately equal. For example, for underfit, I use the equation y equal to mx plus b. This is order of 1, am I right? Polynomial equation, order of 1, which is also called line equation. Now you see, since I chose this, it causes underfit. The line does not fit the data point very well, and this is the only way it can fit. So the error is something like 200. I cannot minimize further, even though if I flip this line in different angle and if I change its position. This is called underfit. Next, if I use this equation, order of 4, okay, order of 4, then my data points all fit very nicely. So this time my sum of squared error during training time is way lower than the testing time, because during training time itself it fit very well. In the testing time, when it sees some different data points, it cannot fit the same way as it appears here. So sum of squared error during training time will be way lower than the sum of squared error during testing time. So this is called overfit. All right, that's the equation here. Now, good fit. What is the good fit? I have to find somewhere between these two polynomial. It shouldn't be like a linear. It shouldn't be like 4, the order power 4. So it should be somewhere between. Suppose if I choose this function and the corresponding equation of the function is this, m1x and m2x square. Now, this is good enough to generate this function, and that fits very nicely by giving very least sum of squared error. That's it. That's called good fit. So when you always say your model is good or better in prediction, you will have to run between underfit and overfit. Assume that underfit is a simple polynomial, like a linear line function. Overfit is like a polynomial function with higher order. So you have to run between these two and find some lower order polynomial with minimal number of terms so that you nicely fit the shape of the data points. All right, that's it. This is called underfit and overfit. Any doubt? Okay, I assume that no doubt.
It's clear, Raja.
Yeah. So deciding the order of polynomial and the number of terms in the polynomial is a painful job, as I already told you. So we go to neural network. I explained. Maybe I don't want to go to neural network. Is there any other way? There are some ways. Algorithms like regularization, boosting, bagging. These are the different algorithms that help to avoid the problems like finding or determining the polynomial and number of terms in the polynomial. All right. However, when your data exhibits very random pattern on Cartesian plane, then there is no way we have to go to neural network. Even though predicting numerical value or classifying some label from the data set, we can apply both in neural network. Apart from underfit overfit, we have to concern one more term, prediction error. Prediction error is not sum of squared error. Okay, sum of squared error is the difference between the prediction value and the observed value. All right, but the prediction error is different. The prediction error comprises three terms. One is bias, which is squared, variance, and irreducible error. Well, let's understand one by one. If you understand bias and variance, which is very hectic to understand and visualize. For example, understanding is also fine, but visualizing is way difficult uh, in a normal discussion. But I will explain very neatly here. First, let's understand bias error. What is bias? For example, I draw some data points like this. Now, this is my line. I fit very nicely. This is the line that gives minimized sum of squared error, but it did not fit the data point very well, right? So there are some left out data points. Suppose this line causes sum of squared error 80. Now it did not fit very well. However, this is the least sum of square error, and this is the case called underfitting, because I know the line did not fit very well, and my algorithm shows this is the least sum of square error. I cannot minimize further. It's over. This is the best this linear function can give now. So it underfits because there are some more patterns to be exploited. Now what I can do? I can increase some extra error such that my extra error, one second, let me choose different color. I increase some extra error such that my line comes like this. In fact, according to linear regression, this line produces the sum of squared error 100. So you can't say this is least squared error. Am I right? Because already there is a line that contains 80. Now you add some error or bias in the sum of squared error that results to 100. However, you see that because I increased some error, it fit the data point very well. We must be happy about it. Am I right? Because we want only good predictions rather than blindly minimizing the sum of squared error. Okay, this 20 is called bias. All right, bias, which is also called bias and then penalty. That's it. So assume that there is a line which is producing least sum of squared error. However, by introducing some extra error, that line can perform good predictions, but error increased. So I can't say it is a least square error, but I can compensate the error to perform better predictions. This is called regularization. In fact, understanding bias, you will understand regularization. All right. You see, the sum of squared error function for simple linear regression is this. I believe that it shouldn't wonder you. This is the observed output. This is the predicted output. I find the difference and then square, sum of squared error. Now, in ridge regression, I did not explain, but just observe that in ridge regression, we add some extra penalty. In lasso regression, we add some different extra penalty, which is called bias. Now, in linear regression, we optimize this. But in ridge regression, we add one more penalty and we optimize the entire this. So if normal regression says 80 is the least squared error, then ridge regression will say 120 is the least square error. It is way bigger, but ridge regression gives good or better predictions. Regression provides bad predictions. All right. So this is how we avoid overfitting. Okay. Easy to understand, right? This is called bias. Assume that bias is some extra error or penalty that you add along with sum of squared error. Okay. And altogether you are optimizing, not just only one term. You're adding one more term to optimize. So to understand these things, we need some more time, 10 to 15 minutes. Okay. This is called bias. If there is a low bias, so adding small bias improve good predictions. Adding high bias, um, also maybe improving predictions, but adding more bias lead to underfitting. What is underfitting? Your data point don't fit very well. Adding very less bias might improve predictions, but it might also lead to overfitting. Okay, what is overfitting? Sum of squared error during training time is very lesser than sum of squared error during testing time. This is called overfitting. So this situation might occur while adding very low penalty or low bias. So the reverse condition of this might occur when we add high bias. That's it. I hope you understand bias now. Now let's understand variance. Okay, variance is very simple. Now sum of squared error during training time and sum of squared error during testing time. If the difference is very huge, then it is called variance. Say, for using line model, let me choose some other color, it is so dull. When I use line model, if I get, say, it is 30 and it is 70, it's called underfitting, am I right? Because it is way lesser than here. The same line model produces, say 80 here. Sorry, this is overfitting. This is overfitting. I'm sorry. This is overfitting. Now, SSC of line produces here 80 and here 40. And this is called underfitting because this is very higher, way higher. Now, if sum of squared error here it is 65 and maybe here it is 60, it is a good fit. Am I right? This is underfit and this is good fit. Suppose if sum of squared error is here 100 and here 780, and this is called variance. It doesn't not only show overfit and also the difference is very huge. This is called variance error. All right, that's it. Low variance in the sense, what is low variance? The difference between here and here will be very less. What is high variance? The difference between sum of squared error in training, sum of squared error in testing is way higher. It's called high variance. All right, it is so easy, right? That's it. Now, irreducible error, one more term. So, regardless of whatever model used with bias, some error can never be minimized. For example, say some patterns is like this. There are different data points and patterns are like this. I use different polynomial function. I use different fancy functions. Whatever I used, I'm not able to minimize the sum of squared error below 30. Okay, so 30 is the least sum of squared error that gives some fitting like this. But still, I can better fit, but I don't know how to minimize. And this is my knowledge and this is my expertise. Below 30, I can never ever reduce. So this is called irreducible error. Below to this, you are not able to reduce it. That's it. Next, bias variance trade-off. In linear models like line, add more bias, but while adding it, you will get the difference. There won't be much difference between sum of squared error during training time and sum of squared error during testing time. So this leads to low variance. Actually, I'm combining everything. You might get confused, but you have to pause the video and then you have to understand word by word. Okay. What I say is adding bias in line model will give you low variance because even though I add more bias, the variance will be very less. But non-linear models like squiggle, even though adding less bias, the variance will be very high. So the trade-off is Low bias leads to high variance. The second case. High bias leads to low variance in the first case for linear model. Maybe I can explain with the figure. If you look at the figure, this is the model complexity on the x-axis, which means that you are increasing the order of polynomial. 1, 2, 3. This is line model, this is quadratic, and this is cubic, and so on. So that's what complexity of the model. And this is error, sum of squared error, or you can just say total error. Okay. Now what it shows us, while while decreasing the bias, the variance increases. Okay. So total error increases, while decreasing the variance, the bias increases. What is bias? We add some extra penalty, so we need to add more penalty. Adding more penalty gives less variance. Adding less penalty leads to more variance. So less bias, more variance leads to more error. So what we need is, we need to find sweet spot that gives us minimal variance and minimal bias, and which leads to very low total error. Okay, so this is what everybody desire. Whoever works in machine learning, they want the minimal bias and minimal variance, which means that you can't increasing the penalty high or you can't decrease the penalty low. You need to include some minimal penalty, and that should minimize the variance. And if it is so, then overall error also will be minimized. That's it. This is called bias variance trade-off. So always remember, bias is a penalty. Adding more penalty gives less variance. Adding less penalty leads to more variance. That's it. You see here, this one and this one. So if you remember this figure, you can nicely attend interview. This is where question will be asked more. And with the figure, I can explain this. You see, this is, as I already told you, the blue color is a training data, green color is a testing data, and here we use a model. Okay, in the first line, I use a model, and the sum of squared error with this polynomial is way lesser than the sum of squared error here. So this is called overfitting. Okay, overfitting in the sense the condition is met way higher, and this overfitting can lead to low bias. So while using low bias, by introducing some bias, can be balance the sum of squared error between here and here by adding some bias here, so that it leads to high variance as well. In the second case, we fit a line. All right. Now the curve can nicely minimize the sum of squared error, but the line, this is the maximum it can do. All right. So the sum of squared error during training time is way greater than the sum of squared error during testing time of the line. So, and this is called underfitting. So we need to find a curve like this to minimize the error. Okay. So underfitting is correlated with high bias and low variance, which means you have to add more bias with this line to make it better predictions. That leads to low variance, the difference between SSE here and SSE here. Initially would be kind of bit of confusing, but you have to recollect the SSE of the both side. All right, finally what I want is this. So maybe it could be approximately here 60. This would be maybe 75 or 45, and good enough. It is very near to 60. So I'm happy about it. And it can give nice predictions because it has understood the data points very well. That's it. Next, hyper tuning the parameter. It's so easy to understand. Now, there is a model that I want to fit on the data point y equal to mx plus b. Now, what I'm going to do, I'm going to approximate the value of m, value of b. Very nice. How? By using the data point x and y. All right. So with x and y, I approximate m and b. Nice. But there are some parameters that are not approximated. For example, ax square plus bx plus c. Now the square value is not approximated. What I mean is ax power m. How do you determine it as square value, cube value, or 4 or 5? How do we know? We can't approximate it. So that's called hyperparameter. In one line definition, a parameter or coefficient that is not approximated or that is not estimated with the help of data point or data set, it's called hyperparameter. We need to tune that parameter such that it produces low sum of squared error. That's it. This is called tuning hyperparameter. In every algorithm, there are some parameters like this, m, and we need to test or tune in different way such that we can minimize sum of squared error because the order or power of a polynomial equation cannot be determined from input data set. That's why it is called hyperparameter. All right. Order of polynomial is a hyperparameter. In cross validation, we say k. So k is a hyperparameter. In neural network, we have so many hyperparameter, number of layers, number of neurons, because the number of layers and number of neurons are not estimated from the data set. We are deciding it, and we don't know whether to set low value or high number of neurons or layers. So we need to tune it so that our model gives better predictions. All right. Sometimes a small subset of training data is used as a validation set. You might have heard about uh, validation data set apart from training data set, testing data set. So if I have a data set like this up to n records, 80% is taken for training and 20% is taken for testing phase. Sometimes some 10% of data set is taken for validation. Okay, validation. So this is used for estimating parameter. Sometimes we use cross validation. Okay, cross validation. Cross validation is a different concept than this. We will see later. Okay, in the next class. This is how we estimate the not estimate. We find the value for hyperparameter. Now, finally, proper fit. When can I call something like a good or optimal model that leads to proper fit? And this is what I want. There are only three conditions. If you meet that, then your model is so good. The first one is you have to balance the bias and variance. You have to some optimal bias. What is bias? The penalty. So you have to introduce some penalty so that your model gives good predictions. And also by adding that penalty, the variance shouldn't be too high. Okay, if I don't add penalty, it gives poor predictions. If I add penalty, it gives good predictions. But it should not be different. The ssc of training and testing should be way different, so the variance should be balanced. The next thing is sum of squared error with training and testing set should be near each other. As I told you, there can be there should not be huge difference. Okay, but some adjustable difference is okay. So this avoids under and overfitting as well. Finally, you have to tune the hyperparameter. So these three should be taken care while building a model in order to find better predictions and also to be called as a better model. Every now and then we get introduced tons of machine learning algorithms. So there are over 500 machine learning algorithms, but we study only the typical models in the textbook. So we can't say all the algorithms give better predictions and so on. It might depend on the data set, it might depend on the problem that we are solving and so on. It's not how fancy some algorithm that you introduce. It should perform very well with testing data by producing good predictions. Okay, sometimes I say sum of squared error is minimized to the very least, but it should provide good predictions. All right, that's it. So before discussing about regularization, which is I already discussed enough about bias, variance, and under overfit. So understanding regularization will not take 5 to 10 minutes. Meanwhile, I will show how to execute the code and then understand the code. I have created two different one. One is the polynomial regression from scratch. We have to write our own code for polynomial regression instead of using a sklearn library. So this is the first code. Import the necessary libraries, and then this is the function I'm going to fit with some data point. Okay, a x square. Now what happens? How I get the value of a? That's what we are going to see. Now I'm not loading any other external data set. Instead, I'm going to create my own data set. Okay. I use some functions, np and range, and then finally I display. This is my data set, single dimensional array that contains -5, -4.9, and so on. Now, initially I create, I execute this. You see there, ax square. I fill 1 instead of a and x square. Here, I'm not using any algorithm to estimate the parameter. I myself assume a is 1. So I calculate, see, I pass each value into x and then I get y in it. All right, like that I call. So corresponding y in it is this value. Next, I introduce some noise with this. Despite this function provides -5 in the sense 25, but I introduce some noise so that squaring 5 gives 27 because there is some noise during the process. Okay, that is the reason I use this line. And finally, I get the y. Now I display, you see here, -5, it is supposed to give 25 because I designed a model a x square and the value of parameter a is 1, but it produced 24.94 because of some noise. So this is my input feature, this is my output feature. Now to display the relationship, if I plot x and y, it shows nice data points like this. You see there how curvy it is. The pattern of these data points exhibit quadratic. Suppose I, by mistake, I try with linear model. What happens? You know this, like using sklearn, we can fit linear model, and then I once I fit the model and I use to predict the x value, so y prediction. Finally, I plot. Now, what happens? This is the model which I got after training and testing using sklearn. All right, regression in sklearn. This is the best fit. You see there. Can you think how much error it produces? But it says this is the best fit. This is called underfitting. Am I right? Because still better you can fit some function, but this is the best fit. Either you introduce some error with this linear function so that it can somewhat fit better than or give good predictions than this line, or try some other model itself. All right, so I'm gonna try some other model, non-linear model. Okay, so what happens here? Instead of fitting like this, I'm fitting like this. Okay, you see the red curve that nicely fits. So what I have done here, I have directly used the y init, which I squared every value. Okay, I did not use any algorithm. Just I'm showing and explaining the model. Now degree 3 polynomial, which is a cubic function. Now how I can do with this? Initially, I create a data set, my own data set. This is the x input, and this is the model I found. Say for the given input x, I used some different algorithm. I found the parameter values of a, b, c, d. But I assumed, I did not do anything like that. To explain you, I assumed a equal to 1, b equal to 1, c equal to 1, and d equal to 3. With this, I calculated y in it. Then I introduced some noise. Okay, noise in the sense some different value than the actual value. We are finding error, no, like that. Then I get the y, then I display them, and this is the x input feature, and this is the y input feature that are processed after with this function. And if I plot the x and y input and output, it shows like this. You see there now the pattern itself is different, not the quadratic. So I can't fit linear function, I can't fit any quadratic function. I have to think differently. Am I right? So first, let me try with linear model. Okay, this is the way we fit the linear regression. Already we discussed enough. So with that, for the training and testing, I use the model to predict the value for the input x, and then I plot it. So this is how it fits, but it can better fit, right? This is the best fit with the linear model, but still it can be better. There are some irreducible error. Okay, you have to add bias so that it minimize. If it's still not able to minimize, you have to try different function. You see there now I try the function like cubic function. So when I use cubic function, and if I get the value a, b, c, d, ax cube, bx square, cx, and then d, how it nicely fits than the linear function. Okay, still, okay. Third one I'm going to discuss is sigmoid logistic function. Hopefully you would heard the term in neural network. All right. So everything is related to, if you know regression, no wonder you can easily observe and understand the neural network. All right, so now the third one is logistic or sigmoid function, which is this 1 by 1 plus e power minus ax. In fact, it is e power minus x. If there is nothing, then the value is 1, right? So a equal to 1, assume in that way. So I have a data set and I use this function to calculate for the every input value, and this is the original value for each x, but I add some noise along with that so that it produces different value. Assume that your model produce different value. Now input and output, if I plot this as a scatter plot, you see there how nicely it produces different pattern. um, to exhibit this, I try with the linear model. I actually train and test, and then I predict for each input x, and then I do plotting. And this is the plot which I got after training and testing. And but still, you are able to guess or observe the some other model can fit very nicely, right? All right. So I try with nonlinear model, which is logistic function. Okay, which is logistic function which I chose. So I choose this model itself. So I'm going to use this y init. I assume that y init is the output for each input x using the model logistic. Assume here I used 1, all right, in place of x. Say that I approximated from input x and y, but for now I did not do any training testing. I assume directly 1. So since I assume this way, my model, you see that the red color curve fits very nicely. Very nice. Now let's do on a real data set. Hope you understood. If you have any doubts, you can interrupt me before I begin this. All right, I go ahead. So let's work on a real data set without sklearn library. Initially, I load a data set which is China GDP. So every year and its GDP. Okay. So after I loaded, I just display the top 5 records, the first 5 records which we discussed in the pandas library session, right? Similar way. There are so many points and so many records, but I just display like this. So here year is a output or dependent variable, and then GDP is a input target. No, it is reverse. Am I right? So it is input. Here it is a GDP, and here it is a year. So kindly change this. So year. Now, you know what is row and column. There are 55 rows and 2 column, year and GDP. Now, as usual, I need to do some exploratory data analysis. For that, I just do scatter plot. If I do scatter plot on the x-axis input, y-axis GDP, I get like this. Definitely, this can't be um, this can't be mapped with a linear model, but some non-linear function. Which one would be suitable? It is not a curvy, so it's not quadratic function. It's not the function like this, so it is not cubic. So which one can be? Maybe exponential. You can observe that initially there is no increase, slightly it increases, suddenly it increases up, and then there won't be any increase if it is. So maybe exponential function or logistic function would be suitable, unless I miss my guess. This is what my initial inference. Very nice, right? Now I do some pre-process and extract the features. For now, I don't have anything to do. And then first step, I go splitting training and testing. Hope you know this. And then I do sort train and test by year. So what happens with the year-wise data? If you randomly choose and if you plot, it'll be zigzag. The answer will be perfect, but while plotting the predicted value here, the curve you see, this curve will be zigzag because the year is not in sorted order. All right. So I do sort by year training and testing set. Then I split myself X train, X test, Y test. Hope you remember this. And then I display. This is what training data looks like sorted by year. This is what testing data look like sorted by year, and then I apply training phase. In the logistic regression, as we know, it should be 1 by 1 plus e power minus ax. However, the power order of the e power can be changed in any way such that it can fit very nicely the data point. It need not be e power minus ax, it can be e power minus a star bx, or anything can be. So now I use this model, okay? I just use this model and then I try to fit. So what I do, I develop the sigmoid function as a code. This is the code for the corresponding sigmoid function. Initially, I decide beta 1, this beta 1 and beta 2 value. In fact, I should estimate beta 1 and beta 2 from the input x and y, but for now I guess or I assume beta 1 and beta 2 like this. With this, what I do, there is a sigmoid function we defined, so I have to pass val, which is a training data, and beta 1, the value I defined, and beta 2. Now I got y training time I predicted for the input feature. Now it is the initial testing. Hereafter I will do the main uh, function fitting. Okay, so with that I just plot for the training x feature x. I predicted the value. So what I mean is uh, for for every data set we have x and y. This is feature. I split. This is for testing, and this is for training. This is for x train, and this is for y train. This is for x test. This is for y test, and I'm gonna predict y bar, the predicted value. So this is y predictor, y pred train, and this is y pred test. After finding this only, we will calculate error. Am I right? So the error is the difference between these two. Y train, Y pred train. Y test, Y pred test. So that's what I indicate here. So I found the value and then I plot like this. So it is somewhat reflect the behavior, but still I can go better. So for that, I'm gonna use a fitting, the sigmoid function fitting. Before that, what I do, I normalize the data. What is normalizing? You see the x-axis, it is year-wise, 1960 to 2010. Y-axis is some value. So I convert all the x-axis values, y-axis values into 0 to 1. That's called normalization. For that, what I do, in the training data of x, I find the maximum value and then I divide each value by the maximum. Similarly, y train, I find the maximum, I divide each value so that all the values are shrunk between 0 to 1. That's it. I'm gonna fit now. So how do I do polynomial fitting manually? There is a library called SciPy. There is a module called curve fit, okay, which is a function in which we have to pass the sigmoid function which we defined. You see, this is the sigmoid function which we defined. We need to pass it, and then training data of x, training data of y. So if you pass this, it will return two values. Okay, it will return two array, one array here, one array here. If you display the array here, if you display the array here, one second, this parameters array, you will get two values. This is called beta1 and beta2 of my function. You see here, this is my sigmoid function beta1 and beta2. That's called beta1 and beta2. And you can display here. So easy, right? Now what I do, I in fact use the same sigmoid function which I defined by passing x train and the value which I found beta1 and beta2. This is called y train pred. Okay, y train pred for the given x train. I need to find the difference, right? Like that. So finally, I visualize the model. Once I fit now, you see how nicely it exhibits the pattern. Nicely, right? Very nice. I cannot fit exponential function. Why? Because here there is a long stagnation of the data along the x-axis and suddenly spikes. But what exponential function says, it's sudden spike. For example, if you Google it, exponential function, you see there'll be sudden spike, and you see here it spikes very nicely. Okay, it spikes. So that is the reason if we use logistic function, and most of the time it is very close to zero. And also you have to observe this. You see there, it is close to zero. It is close to zero, but our data point is not close to zero, just away about the zero on the x-axis. Okay, what I mean is, if I go to polynomial, you see here it is not exactly zero. It is just about zero because the GDP cannot be zero, right? Above zero. So we can't use the exponential function. And finally, if I plot the prediction for what I plot here, you see there the observed y train and the predicted y train for the input x train. So that is what I plot here. So the green color is the GDP observed for the corresponding x, and red color is the GDP calculated for the corresponding x. This is called year. Okay, down there year. So it is now, it is nice. We have almost depicted a built a function that matches the pattern. And residual plot, as you know, most of the time for polynomial function we need not put residual plot because the residual plot for polynomial is completely random. But you see here it exhibits some pattern, some kind of it starts here and it comes over here. And so with this you can't understand much even if you display the residual plot. All right, so you need not rely on this. And then I calculate sum of squared error. Hope you know everything. Okay, I need not to explain. There are different way of calculating error, enough using any one. So I have given how to calculate with all different options, but it is enough to calculate with only one. And then testing phase, now with test data I do the same with the estimated function. What I do, the curve fit, and then I pass my function, and with x test and y test. What is x test, y test? This is x test and y test. I'm going to find y pretest. So I find the parameters, and the parameters for the training testing data is this beta1, beta2. Again, I do the same thing with my sigmoid function which I defined. I pass x test with beta1 and beta2. I find y pretest, and I plot this again. It gives nice so that I'm not leaving out anything. Okay, Now, what I do, then plotting observed GDP and predicted GDP. Again, I plot this function. It looks very nice. Residual plot. Simply I put, not for any purpose. And then I calculate different error functions. You know this. And finally, I calculate R square value, and it is 94%. Finally, I display everything. SSC. So SSC is, you see, almost way equal. So my model has done pretty nicely. All right. And other thing also, they are very close, which means that bias and variance are kind of very uh, traded off, and they are very equal to, so that my model is good. And R square value also is very nice. This is called polynomial regression. Hope you understand. Now this is the same thing, but I'm gonna do with sklearn. So it won't take much time because we already discussed enough. So what I do now, I imported all the necessary libraries. And linear, first I do with linear regression. I generated some data set. For now, I plot the data set. It exhibits this data point, which means shape. Now fitting with simple linear regression. So I use the sklearn library. I fit them. I predict the value for x. For in this program, I did not split training and testing. Instead, I use the whole x as a input and whole y as output. I did not split, so that it is enough to understand, right? You can do later splitting training and testing. It takes me a lot of time. So after fitting, you can get the b value. This is m value. I'm fitting y equal to mx plus b. So this is m value, this is b value, and this is my equation. You see I displayed y equal to mx plus b. Now I display the model and it shows the pattern like this. I'm not much satisfied. So I calculate the SSE, it shows like this, and then I calculate R square, it shows the 65%, which is not desirable. So what I do, rather than believing linear, I go with polynomial with degree 2. What does it mean? Y equal to mx plus b is polynomial with order 1 because x value is power 1. But now I'm going to find ax square plus bx plus c. That's called power 2. Now again I produce some input data set, which is this shape. Now with all polynomial order 2, I'm going to fit. Observe this only one, and this is same. This coding is same. Only this value you have to change for the upcoming models. So what I do, I import a library operator and I import polynomial features, which is going to help us to fit polynomial function. And there I import pre-processing. All right. Now what I do, uh, I use polynomial features by passing degree equal to 2. This is called quadratic equation model 2. Now I get the reference address here, and then using this polynomial features, I fit the input feature x, and I got some output with x poly. What I do, I have to import linear regression, and fitting the linear regression model, I have to pass x poly and then the output feature y. That's it. This is called fitting polynomial. Okay, here also we use linear regression, but before that we do one step in order to fit the polynomial functions on the data points. So these are the steps. Okay, early we did by manually, now while doing with library, and this is the shape. All right, now we got the whole is considered for training, and this is for the thing which we pass as an output observed value, and we are going to get the predicted value. All right, now what I do, i predict the I predict early. I have only y. Now I'm going to find y cap. The y cap is y poly pred, and I'm predicting it. Now I display the features. Now you see a x square b x plus c. This is the value for a, this is the value for b, and this is the value for c. 0 indicates that the term c is eliminated from the equation. So this is what the equation, ax square bx and c is eliminated. C is eliminated. All right. So this is a b c. This is what I estimated. Now I visualize the performance. What I do, I plot y pred and y. So it shows that such kind of fitting, but still I'm not okay with that. Maybe I can increase the order of polynomial. I'll try that. So I compare with the earlier model which I fit linear. This is linear and this is quadratic. I calculate for SSE for the quadratic. I calculate R square for quadratic and I record it. Okay. Now pretty improved. Last time it is 64%. Now it is 74. But this is not good enough. And now let's see polynomial regression degree 3. Okay. Same step. I create a data set. I visualize it. Now this time the step which I explain, only one change I do is from 2 to 3. It's called cubic function. Ax is cube plus bx square plus cx plus d. So I'm going to estimate four parameters. So I fit everything and then I'm going to predict it. Finally, I get the coefficient value. So what is that? This is a value, b value, c value, and d value. Now I'm displaying a x cube, b x square, c x, and d value is 0. It is ignored. The value is 0. Now with this model, I pass my input X and then I'm going to show the fit, okay, by using that. So now I'm plotting Y predicted and then Y observed. So this is the model you see. Using cubic function, how nicely it fit all the data points. Very nice, right? So good. Now I display all the model, whatever I found. The red color is a linear and the green color is a polynomial 2, and you see the purple color is polynomial 3. Very good. I calculate SSE for polynomial order 3. R square. You see the R square, now it reached 100% because it has fit nicely. So you see there it has fit all the data points, leaving out anything, without leaving anything. So 100%. Now I go with order 20. The same step. I create a data set. I display the data set. It shows like this. Now this is the same step, fitting the polynomial, but instead of 3, 2, and 3, now I give 20. That's it. I actually predict the value for y and the parameters. So it is 20 coefficients. Am I right? You see 20 coefficients starting from bottom and the last value. So I can't display as a equation because there are 20 parameter coefficients a, b, c, d, e, f, g, and so on. Now I show. Now this time when I show, you see I increase the order of the polynomial x power 20, but you see there are some misfit. Okay, you see there misfit. Now I display all the model which I got so far. Red color is linear and then polynomial order 2, order 3, now order 20. Order 20 is somewhere missed. So I calculate SSE and the R square. You see R square reduced. So polynomial order 3 fit nicely, but polynomial order 20 somewhat missed 1%. Now let's see with degree 40. Same data set, I visualize it and I fit with order 40. Now degree order for just change over here and the remaining steps are same. I predicted this time there are 40 coefficients or parameters. Okay, starting from here ax power 40 and bx cube, bx power 39, cx power 38, and so on. Now I display, you see there, this is the result of, actually this is 40. Okay, this is 40. This is the result of polynomial order 40. You see so many missings. Here also missed the data point and so on. So what I did, I plot all the curves, whatever I found so far. Polynomial 40, 20, 3 to linear. So I calculate SSE for order of 40 and R square. You see there, R square drastically reduced to 91 from 99. So I compare the overall performance here. So I displayed SSE and root squared R square value for linear polynomial 2, 3, 20, 40. So as you observe here, the sum of squared error has been minimizing when you increase the order. It reached But when you increase the order while increasing the order up to 3, it minimized. After 3, it started increasing and it keeps on increasing. All right. Look at the r square value. R square keeps on increasing. After a point, it keeps on decreasing. So this is called underfit and this is called overfit. And what we want is the fit which is in the middle. All right. Yeah. You got everything, all the idea. So this is how we do. With respect to neural network, you can't visualize like this because in neural network, we don't display the parameter value. You see here, as we increase the number of order, the estimated parameters are huge, 40, because the order of polynomial is 40. But in neural network, we use the matrix of huge based on the input size, am I right? And the number of neurons in the first and subsequent layers. So we can't visualize just like this. It's so complex in neural network. However, we can finally see like this. Only one curve and the sum of squared error loss minimization. That's it. Okay. So I guess that the lecture is too long today. Okay, we finished polynomial regression. So tomorrow again we will have one more session around evening time, maybe 4 or 5 o'clock. So there we will discuss about lasso and ridge regression, and then one more topic. What is that? Yes, we finished off polynomial, overfitting, underfitting, bias, and we need to discuss this and the remaining three topic. Tomorrow we will discuss and finish off. Okay, thank you.